We're looking at continuing on now in Unit 3 in our dosage calculations. We've talked a lot about solution concentrations and diluting solutions and mixtures. Today we're going to talk more about those concentrations and how they're calculated. But I want to review a little bit about what we've done the last couple of days. First, let's look at a question like, how much 7% solution is created by diluting 350 milliliters of 13% solution. So the big formula we had that governed a problem like this was that change of concentration formula or concentration adjustment formula, where it said we had an initial concentration times the initial volume, so C1 times V1, and that had to be equal to a final concentration times the final volume, so C2 times V2. Remember that expression, C1 times V1, represents the amount of active ingredient or the amount of serum that is in that solution. So if we're just simply adding a diluent, like normal saline or sterile water of some sort, we're not adding any active ingredient. So the amount before and after that dilution should stay the same. So for in this case, we have 350 milliliters of 13% solution. So our concentration is 13%. Now remember we said you can either just leave it as 13 or we can make it that rate of 0.13 times the volume of 350. Over here for the concentration, now since we left the first one is 13, we're going to leave this one as 7. We don't want to, whatever we do to one, we have to do the same to the other, times whatever this final volume is. Now we just have to solve the equation. So we'll start by doing 13 times 350, which gives us 4,550 equals 7 times V2. And of course, we solve this equation by simply dividing by 7. So 4,550 divided by 7 gives us 650. Now that's V2. Now remember, whatever unit V1 was, V2 has to be the same unit. Well, V1 was 350 milliliters, so V2 is 650 milliliters. So from 350 milliliters of 13% solution, if we dilute that down, we will get 650 milliliters of 7% solution. We saw other problems like how much sterile water should be added to 240 milliliters of, let's go 18% solution to create 15% solution. So again, we're looking at that same formula. C1 times V1 equals 2 times V2. And we're plugging in numbers. So C1, V1 is just the one that we have both numbers of. So we have 240 milliliters of 18% solution. So 18% times 240 equals, once again, we have 15% times V2. So we combine 18 times 240, 4,320 equals 15 times V2, and we divide by 15. divided by 15, we get 288 is V2. Now, again, this is where we had to be careful to make sure we've answered the question. Volume 2 is 288 milliliters. But the question was, how much sterile water should be added? So the final volume is 288, but the amount of sterile water is that final volume minus the initial volume of 240. Because all we've added is the NS, or sterile water. So we subtract, we get 48 milliliters. The total change in volume is accounted for by the NS. So we add 480 milliliters of NS. But we also looked at dilutions and how dilutions fit in. And we might look at, find the new concentration. If 24% solution is diluted 3 in 8. So 3 in 8 dilution means we have 3 parts of serum, or 3 parts of the concentrated solution, 8 total parts. Now on the other side, if we're trying to change the concentration, the larger concentration goes with the larger number. 24% would be the larger concentration. After it's diluted, it'll be less concentrated. 24% goes on bottom, and we'll cross, multiply, and divide. So 3 times 24 divided by 8 gives us 9%. So that new solution will be a 9% solution. Or we might ask, find the dilution required. To dilute 56% solution to 21%. So remember, to find the dilution required like this, it's just a matter of taking the 2%, so the smaller percent, the diluted concentration would be the smaller percent, that's 21%, over the larger percent, the 56%, and reducing this to a ratio. So the percents cancel out. Looking at 21 and 56, both of those can be divided by 7. So 21 divided by 7 is 3. 56 divided by 7 is 8. So that's 3 to 8, which makes it a 3 in 8 dilution. So for every 3 parts of 56% solution, we'll get 8 parts of total solution, of 21% solution. So we've been talking about this concentration, this idea of concentrations in solutions for a while. Let's talk about what it means to be concentration, what a concentration is. And to do that, we first have to talk about quantities and some properties of those quantities. One of those properties is being additive. Additive means the 2 amounts combine to make a total amount. So in other words, if I have 8 units of one and I add 5 units to it, I get a total of 13 units. That's additive. Well, you might think, well, isn't everything additive? Well, when we get into chemistry, one thing that's always additive is mass or weight. So if we're dealing with the standard system, we're usually focusing on weight. If we're dealing with the metric system, we're generally focusing on mass. If I have 42 milligrams of one substance and I combine it with 28 milligrams of another substance, I simply add 42 plus 28 to get 70 milligrams total. That is always additive. Sometimes additive are solutions. And the ones that are additive are solutions that have the same base or same solvent, the chemical term for it. So if we have two alcohol-based solutions, they would be additive. Two water-based solutions, they would be additive. So if I'm combining two water-based solutions, they might be different concentrations. Let's say I'm looking at a 24% solution and a 41% solution, but they're both water-based, so they're both some sort of serum in water solution. Well, if I have 120 milliliters of the 24% solution, and I'm adding that to 250 milliliters of the 41% solution, they will add up to 370 milliliters. So sometimes additive is the volume of those solutions. Usually not additive, or that we can't count on being additive, is general volumes. And where this really becomes an issue is if we're looking at some sort of a powder-based serum. And we're putting into some sort of a liquid vehicle or liquid solvent, we should say, liquid solution. For example, if I were to add 10 milliliters of salt to 80 milliliters of water, your instinct would be to say, well, that's going to end up with 90 milliliters of salt water. It does not. It actually ends up with about 94 milliliters. Or not 94, 84 milliliters. Sorry about that. Come on. 84 milliliters of salt water. And this is true with any sort of powder that dissolves into a liquid solution. The volume is not additive. The total volume ends up being less than the sum of the two parts being added together. And the reason for that is because we have particles of water. Now, a lot of people don't think of particles of water as having gaps between them, but they do. Particles of water are actually kind of oblong. And as they sit together in that solution, when they sit together in their container, I should say, there are small gaps between those particles. So when we add that powdered serum, the particles of the powdered serum are able to hide in those gaps. Now, sometimes we can add some powdered serum to the water and not increase the volume at all if the size of the powder is smaller than the size of the gaps in the water. If it's bigger than the gaps in the water, then it pushes the particles apart just a little bit, and that's what increases the volume. Of course, now there's a limit. There's a solubility limit. Not a term we need for this class, but that means we filled up all the gaps in the water. Well, then at that point, the powder won't dissolve anymore. It'll settle to the bottom, and it does increase the volume at that point. So when we're dealing with volumes, we have to be careful. We can't talk about combining two volumes and getting a total volume. We have to be careful that we know that those things are additive. If it's two water-based solutions, we know they're additive. But if it's a powder being placed into a water-based solution, it may not be. In most cases, it will not be. So let's start with the simplest one, the one that always works. And it's out of habit, it's still called a weight-in-weight solution, or concentration. Abbreviated W/W, weight in weight. Now, of course, as we're switching over to the metric system, and most of what we're doing in here will be metric, it really should be mass in mass, because we're dealing with mass, not weight. But we've left the old notation of W/W. So the first one is the serum is being measured in weight. And the second one then is the total solution. So if we have a weight-in-weight solution, of course measured as a percent, percent weight in weight is just equal to the units of the solute or serum over every 100 units of solution. So what does that mean? Well, let's say we have let's say we have 9 units of, let's go with morphine, powdered morphine, in 50, I'm going to change this here. Since we're saying it's weight in weight, let's do this. 9 micrograms of powdered morphine in 500 micrograms of water. So this is 9 in 500. Now I'm going to put the units in here for now just because it's important that we make sure these two units are the same. They're both micrograms, so we're good here. We want to make this a percent, so I have to figure out what is that out of 100. So we can cross multiply and divide. 9 times 100 divided by 500 is 1.8. So 1.8 out of 100, or 1.8%. So that would be a 1.8% solution as far as the concentration. Let's say we want to make 200 grams of 12% sodium chloride, an NaCl solution. So remember that 12% means 12 grams out of every 100 grams of total solution is sodium chloride. So if we want to know how much sodium chloride is needed, well, we just set up the proportion. 12 grams out of every 100 grams is sodium chloride. We're going to make 200 total grams here of total solution, and we can cross, multiply, and divide. 12 times 200 divided by 100 is 24 grams of sodium chloride. If we want to know how much normal saline we need, well, because we're dealing with mass here, it's additive. So we can just go ahead and subtract total solution of 200 grams, that's this amount, minus the mass of the serum, of the sodium chloride. And that subtracts me 176 grams of sterile water that's going to be combined with that. We might ask, find the concentration. If 400 milligrams of serum is combined with 160 grams of NS. And I should have said find the weight and weight concentration. Specify that. So for our weight and weight concentration, it is the weight of serum. Well, we have 40 milligrams of serum combined with 160 grams of NS, but we have to add that to, remember, it's the total amount that goes on bottom, just like a dilution. 40 milligrams. So on top, I have 40 milligrams still. I need to change this 160 grams to 160,000 milligrams plus the 40 milligrams. So now we all have the same unit of milligrams, so we can cancel those out. This is 40 over 160,040. And we can divide that out. Or we can do, we know the percent is going to be out of 100, so we can cross multiply and divide. So we'll do 40 times 100 divided by the 160,040. Give us 0.025, basically, out of 100. That's 0.025%. Typically, some of our stronger medications are really strong antiseptics, like zinc chloride, or some of those are down to under 0.1%, or even in this case, it's a few hundredths of a percent concentration. We might ask, how much NS should be combined with 80 milligrams of serum to create let's just do 10% weight and weight solution. So again, weight and weight. So 10% is going to be 10 out of 100. We have 80 milligrams of serum, so that goes on top. We cross, multiply, and divide. 100 times 80 divided by 10 makes this 800. Now this is milligrams because the 80 was milligrams, but this 800 milligrams is total solution. So to find the amount of NS, we take the total solution minus the 80 milligrams of serum. So it would be 720 milligrams of sterile water being added to that serum. So I started with the weight and weight, or mass and mass solutions, if you will, because they're the simplest, because they are what we're used to. Everything adds up. Well, the next thing to talk about is volume in volume solution. Or abbreviated V/V. So again, the first volume is the amount of serum. Second volume is the total solution. Now remember here, we have to be careful because volumes may not be additive. So if we're looking at find the amount of 6% solution that can be created using 150 milliliters of syrup. So 6% solution, 6 out of 100, 6 parts out of 100. The 150 milliliters of serum, that goes with our serum is the top number, the 6. And we can cross, multiply, and divide. 100 times 150 divided by 6. I believe that's 2,500, but let's double check me. It is 2,500. First, that unit would be milliliters. And now this is total solution. In this case, I cannot calculate how much water or NS would be added to that because I don't know if the serum is powdered or if it's already a liquid solution or whatever it is. I don't know if they're going to add up. So what the process there is to take whatever measuring device, whether it's a beaker or graduated cylinder, to put in the serum first, 150 milliliters of serum first. That would go on bottom. And then you would simply fill with sterile water until you hit that 2,500 milliliter mark. And once you hit that mark, you have reached that point. Now, as you're adding, as you're putting water in, you should be careful to stir it, mix it regularly. After you mix it, you wait for it to settle down to see whether it stays in solution or not. Believe it or not, when you stir a solution, the volume actually changes until the particles calm down. So for a volume in volume solution like this, it can be very tedious to mix because you do have to worry about that additivity of volume, that conservation of volume, or non-conservation of volume, if you will. We might ask how much serum is needed to create 120 milliliters of (18% volume in volume solution. So 18% is 18 out of 100 again. On the other side, we're creating 120 milliliters of that solution. We'll put 120 milliliters on bottom, and we can cross, multiply, and divide. So 18 times 120 divided by 100 is 21.6 milliliters. So we would need 21.6 milliliters of serum. Now again, I don't know how much saline would go in there because those numbers do not add up. You would just put in the 120 or the 21.6 milliliters of serum, and then you would fill till you got a total volume of 120 milliliters. So finally, we have weight in volume solution, abbreviated W/V. And again, probably should be listed as a mass in volume solution because we're using metric units now, and metric focuses on mass rather than weight. So the weight or mass, again, is our serum, the amount of serum, and the volume is the total solution again. So one thing to keep in mind here is if you go back to Unit 2 when we talked about the definition of a milliliter. 1 milliliter of water is the definition of 1 gram. So we have to be careful here with our units. The weight or mass is in grams. Well, the volume should be in milliliters. So we might ask you to find the concentration if 9 grams of serum is in 200 milliliters of solution. I should say of weight and volume solution. So we're looking for the concentration, some sort of blank out of 100. We have 9 grams over 200 milliliters. This is the combination of units we need. We need grams for the weight, milliliters for the volume. So we can just cross multiply and divide. 100 times 9 divided by 200 is 4.5. So 4.5 out of 100, or a 4.5% solution. So be careful here if we ask find the concentration. If 250 milligrams of serum is in 200 milliliters of solution. Now, at first you say, well, it's 250 over 200. That's more than 100%. But remember, we have to be careful with our units. The volume's in milliliters. That's what we want. But the weight is in milligrams. So remember, we want that to be in grams. 250 milligrams becomes 0.25 grams. So to find this concentration, blank out of 100 is our concentration. 0.25 grams of serum in 200 milliliters of total solution. Cross, multiply, and divide. So 100 times 0.25 grams divided by 200 milliliters gives us 0.125. So that's a 0.125% solution, or 1/8% solution. So we can see those concentrations. It's not terribly difficult to work with. We just have to be careful that we know which ones are additive. Only the weight and weight is truly additive. Everything else, we have to talk about what we're starting with, the serum and then the total solution. We can't find the amount of saline to add. And then we have to make sure our units are fine. And that weight in volume, we have to make sure we're dealing with grams of weight per milliliter of volume. Now, the next thing we want to look at here is we want to look at how do we fill the syringe. We got to deliver this medication to a patient, whether it's going to be an intramuscular injection or intravenous injection, or if it's going to go into just directly into an IV. It's already hooked up to an intravenous site. So we need to know how do we figure out the volume. So these are mocked up syringes here. And for these, we're going to look at how do we calculate, or first of all, how do we read how much is in a syringe? And to do that, we have to look at the labeling on the syringe. So let's say this is in milliliters. This is labeled 1, 2, 3, 4, like that. So to figure out, we need to figure out what each marking on the syringe stands for. So what we do is we look at two labeled markings. That would be the 1 milliliter and the 2 milliliter here. We try to avoid the 0 milliliter because a lot of times at the beginning of the syringe it's tapered and it's really hard to see. Those first couple of markings might be absorbed in that taper, and so it might be really difficult to see what those first ones are. So typically we'll start from 1 and go to 2, or from whatever the second labeled marking is and go up to it. So from 1 milliliter to 2 milliliters, that's 2 milliliters minus 1 milliliter, is 1 milliliter of volume. How many markings are between there? 1, 2, 3, 4, 5. Then we know that the same over here, but I'll label them 6, 7, 8, 9, 10. We can speed up that counting by knowing this is halfway and just doubling the 5 to get 10 markings. So 1 milliliter over 10 markings, so 1 milliliter divided by 10 is 0.1 milliliters per marking or per space on this syringe. Now if I fill this syringe with some sort of serum, right about there, it's closest to this marking right here. So first of all, we find the label that's either below it or above it. We either start below it and count up, or start above it and count backwards to it. Here it's easiest to go below it to the 3, and each of these is 0.1. So this would be 3.1, 3.2, 3.3 milliliters. So that syringe is filled with 3.3 milliliters of fluid. Let's look at another syringe here that's labeled like this. Again, still milliliters. This is 1 and 2. So once again, we'll look at the two labeled markings. That is from 2 milliliters minus 1 milliliter is still 1 milliliter of fluid. But now if we count between them, there's 1, 2, 3, 4, 5, 10, 15, 20 spaces. So 1 milliliter divided by 20 spaces is 0.05 milliliters per space. So if this syringe was filled up to here, so the closest marking is this one right here. We wouldn't want to start at 1 and count up because that's a lot of counting up. But we could start at 2 and count back. So that's 2. This would be 0.05 less, so 1.95. 0.05 less would be 1.90. This would be 1.85 milliliters. So that is holding 1.85 milliliters of fluid. We could have it labeled, go like this. Again, milliliters. Now, of course, we don't have a 1 marking here, so we're going to go from 2 to 4. 4 milliliters minus 2 milliliters is 2 milliliters. Now we count. There's 1, 2, 3, 4, 5 spaces in between. So 2 milliliters divided by 5 means it's 0.4 milliliters per space. So now if this syringe is filled like that, so this is the closest marking that it's to. This one we can either start at the 12 and count up, or the 14 and count back. It is usually easier to count up if it isn't too big of a difference. So I'm going to start at the 12. That's 12. This is 12.4 because each space is 0.4. This is 12.8. This is 13.2 milliliters. So it's very important when working with a syringe, any scale of measurement, by the way, that you first take the time to figure out what each marking, what each space represents, so that you can accurately read the full output. Now let's talk about comparing syringes for a second. If I needed to administer 1.2 milliliters to a patient, and I had the option of 2 syringes, this one here, where I have 1 and 2 milliliter marks, or this one down here. Now let's put them together here. So 1.2 milliliters is what we're administering. This one is milliliters. 1, 2. This one's also milliliters, but it's labeled like that. Which one would I want to use? Well, you might say, well, it doesn't matter because this one here, I can fill it to 1.2 like that. Or this one here, 1.2. I read the markings, it goes to there. And yes, in a perfect world, either one would work just fine. But in practice, you prefer to use this one. Why? Well, it's because of the structure of the syringe itself. These numbers being further apart means that the syringe, each position of the syringe is a smaller volume, and that generally means that it's a narrower syringe. It's a thinner syringe. One like this where it gets as a higher volume, that's actually probably a wider syringe. And if it's wider, if I'm off by just a little bit, and this wide syringe being off by just a little bit, the amount of fluid or medication that's in that narrow little band is a much higher volume than the same amount of fluid that would be in that narrow little band on a narrower syringe. So we always want to use a syringe when we're trying to measure a medication that's going to be close to full. Now, if we had a third option, it looked like this, 1 milliliter there, we would not want to use this one. Even though it's an even smaller, narrower syringe, 1.2 milliliters is not going to fit in here. We don't want to have to inject the patient twice to get the medication into them. So we'd want to go with the bigger syringe that we can get a single injection in. But that error or a possible error in the syringe is something to be considered. A full syringe is always more precise than one that's just got a little bit in it because of that. Okay, so for Friday, page 146, 1 through 17, the odds. That is dealing with the solution concentrations. And page 168 through 169, 1 through 19, the odds, looking at reading syringes. With that, you guys have a great day. We'll see you all on Friday.